All right, folks, it's Bass Action, back in action here. In this video, we are going to go through some inscribed angles, but then also we're going to cover a whole bunch of properties of circles up here at the top. So what you need is your gold foldable just closed in on the front of it, and I'm going to cover all of these properties, and then we will do additional practice with this, applying all of these together. So you won't typically see one individual property. Normally you'll see multiple of these properties all within the same problem, and you have to kind of pick and choose. So we're going to actually start here at the bottom, okay? And down here at the bottom is an important summary, and although we haven't done all of these, we will eventually. These four possibilities of where the vertex of an angle might be on a problem are going to be the four main ways that you're going to analyze arcs and angles in our circles. Now, the first one that we have already done is when the vertex is on the center of the circle. That's called a central angle. So if the vertex is on the center, then what happens is that the measure of the angle and the measure of its intercepted arc are the same. Remember, the intercepted arc is the portion of the circle being the ring, it's the portion of the circle that is inside the angle. So if you extended the sides of your angle, it would be what part of the circle is inside that angle. So when the vertex is on the center, the angle and the arc are the same. Now what we're going to look at is what happens when the vertex of the angle is actually on the circle itself. So you can see in the two pictures that I have here, I have an angle with the vertex that is on the circle, and I have another angle where the vertex is on the circle. Now, this angle here on the left, this one on the left, is called an inscribed angle. And an inscribed angle is when the vertex is on the circle and the sides of the angle are actually chords of the circle. This is where that vocabulary that we did earlier is really important. The sides of the angle are chords. Now, on this picture over here, the vertex is on the circle, but only this one side of the angle is a chord, and this side of the angle, or if we went this way, this side of the other angle, is not actually a chord. However, if the vertex is on the circle, the formula and the relationship is going to be the same if it's an inscribed angle and even if it's not an inscribed angle. What matters is where is the vertex of the angle. So if the vertex is on the circle, then the measure of the angle, okay, so the measure of this angle right here is going to be half of its intercepted arc. So if my arc is x, then the measure of my angle is going to be 1/2 x. Now, what's important to recognize is that we're going to have to be able to go in both directions. So let's look at this picture over here. Let's say that I knew the measure of the angle and the angle itself was x. Then the measure of its arc, in this case it would be this arc BC, then the measure of its arc would be 2 times the angle. So depending on the direction you go, you have to think whether you should be getting bigger, moving out to the circle, or whether you should be getting smaller, moving into the angle itself. Okay, this idea right here is going to apply to many of our properties up above. So I'm going to make reference to that vertex on the circle, that inscribed angle, quite a few times. Now, up here on the top, there are several properties here that you want to consistently be able to mark in your picture and always be looking for these as possibilities. So property number 1 would be that all the radii in a circle are the same, okay? So these two radii of the circle are the same. The reason why this is going to be especially important is because if we drew in this chord AC, what we would notice is that we actually have an isosceles triangle. So always looking for those potential isosceles triangles will be important. The next property says that if two chords are congruent, so let's say that DE is congruent to GH, okay? If two chords are congruent, then their intercepted arcs are congruent. So arc DE and arc GH, these are also congruent to each other. And even more, if we drew in these central angles, and you should be drawing these in on your picture as well, if I created a central angle using those arcs, then the measure of this angle right here is going to be congruent, if I drew in the other central angle, would be congruent to this central angle there. So congruent chords will give you congruent arcs and will also give you congruent central angles. The next one is that if inscribed angles intercept the same arc, then those angles will be congruent. Now, that's pretty wordy, but let's take a look at our picture here. So I'm going to do a little coloring, and assuming you're not colorblind, and if you are, you could maybe use bolding or something like that to help distinguish the arcs. So from this vertex O, I'm going to color this angle right here. I'm going to extend it. And what I'm going to see is that I have this intercepted arc right here. Then I'm going to look at this angle P, where P is on the circle, and I'm going to extend its sides. So its intercepted arc is right here. Notice that their intercepted arcs are the same. So if I knew the measure of this angle, I would double it using the inscribed angle property to get the measure of this arc, but this arc would be the same as the blue arc, and then I could divide by 2 and get to angle P. So angle O and angle P have to be congruent to each other. Now, properties 4 and 5, we're going to do more with this in class, but properties 4 and 5 are referring to the perpendicular from the center of a circle to the chord will bisect this chord. So you can see I've drawn in these little dotted lines to help you better visualize a perpendicular, because sometimes those are a little bit difficult to rough in. So if this is perpendicular, okay, then what should happen is it's going to bisect that chord, okay? And on the other one, on GH, its chord should get bisected as well. Now, you'll notice that I used the same number of tick marks on each of these, and that's what I'm going to point out right here. I'm going to come back to the other part of that property in a moment. I used the same number of tick marks here because if two chords are congruent, so if DE is congruent to D8 or GH, then these little distances should also be the same. Now, the converse will be true. If I only knew that the distances were the same, then I would know that the chords were the same. Now, I will just tell you, I know this property right here can be kind of overwhelming to take in, and we are going to do more with this in class. So don't worry if you feel a little overwhelmed on this property 4 and 5. The last thing that I do want to notice, though, want you to notice is that even though in addition to the chord being bisected, that the arc itself is going to get bisected as well. So if we had extended this farther on, then that arc would also get bisected, okay? Now, moving on to property number 6, parallel lines will intercept congruent arcs. So we're going to mark these lines here as parallel, and then we're going to think through why this should be true. What we're going to do is we're going to draw in a transversal. So we're going to draw in a segment TW. Now, last semester, what we did is we would look at this little Z. We would make a little Z to help us find some alternate interior angles. And we would notice that these two angles here were congruent. Well, if these two angles are congruent, we're thinking back here to this property number 3. If angles are congruent, then their arcs are going to be congruent. And if the arcs are congruent, then the angles are congruent. It goes both ways. So if these angles are congruent, then the arc the intercepted arc for that angle, SW, should be congruent to the intercepted arc for this angle W, which would be TU. So be looking for those parallel lines. The next one we're going to look at is going to be inscribed angles in a semicircle are right angles. Again, very wordy. So I've got a circle here, I've got a diameter. We're going to draw in an inscribed angle, okay? And we're going to start here with this point W, and we're going to connect it to Y, making a little chord, a very tiny one, and I'm going to connect it to Z. Now, what this is supposed to be telling us is that we've created an inscribed angle, and the intercepted arc is a semicircle. It's telling us that our angle must be a right angle. So let's think through why that would be true. Going back to our inscribed angles being the angle and the arc, we understand this relationship is the angle is half the arc. Then if we come up here, if we know that this arc here is 180 degrees, then its angle should be half of that, which would make it 90, or a right angle. Now, what I do want you to notice is I want you to draw in one more. We're going to look here at angle X, and we're going to connect it again. So I'm going to connect it to Z, and I'm going to connect it to Y, making a nice inscribed angle. Now, this angle also is going to be a right angle because its intercepted arc is 180, so the angle would be 90. But what I want to draw your attention to is that these two triangles are dramatically different. So yes, they are both right triangles, but no, they are not congruent. The next one that we're going to look at is property number 8. And again, it's kind of wordy. It says that opposite angles in a cyclic quadrilateral are supplementary. Okay, well, we understand opposite angles, so those are going to be across from each other, and we understand supplementary. So let's break down what cyclic quadrilateral means. Cyclic quadrilateral means a quadrilateral where each vertex of the quadrilateral is on the circle. It's called an inscribed quadrilateral. Inscribed, so each vertex is on the circle. So what this is saying is that these two angles right here, N and R, are going to be supplementary. And I have an activity in your notes that will break this down better for you if you're having a hard time. And these two angles will be supplementary. They're not equal, they're supplementary. Now, the very last one, what you're going to do is you're going to kind of rough it in, and you might need to pause the video. But this one is saying that if I can draw a perpendicular bisector of a chord, so notice this time my chords are very different. So I've got a chord right here, and I'm going to rough in a perpendicular bisector. Now, I'm just going to rough it in. It'd be nice if I had a ruler, but I don't have one handy. But that's okay, because the cool thing about this is that even getting just close makes it pretty believable. So I've got a perpendicular bisector here. What this is telling us is that that perpendicular bisector is also a diameter of the circle. So what it's saying is that this portion right here is a perfect diameter. Now again, mine was a little bit rough. Now we're going to do one more. I'm going to take this PQ and I'm going to rough in a perpendicular bisector again. Perpendicular, make sure it bisects it, use a different number, and it's saying that this also should create a nice diameter. The beauty of this is that if we have two of these perpendicular bisectors and thus two diameters, what we know then is that their intersection is the center of the circle. Okay, that's a lot of properties, and again, you're going to do a little bit of practice with this to start to get them under your belt, and then we're going to do a lot of practice in class.